Video we're going to look at the Taylor series expansion, but before we do so we're going to look at the mean value theorem. So we begin with a function f of x which has some curvature to it, and we choose 2 points on the x-axis, a and b, and this is a closed interval, and we're going to pick a chord. So we have f of a and f of b. And we're going to pick a chord between A and B, and we find the slope of that chord is equal to the rise over the run, which is f of B minus f of A divided by B minus A. That's the slope of that particular curve of chord. If f of x is differentiable over the closed interval AB, then there's a point where the slope of f of x is equal to the slope of the chord, and that occurs at some x star, and at that point we get the following. We get a curve that looks like that, and it's tangent to the function f of x at that point x star. And we also have this f of x star at that point. Now, at x star, we find that f prime of x star, so the first derivative of the function f of x at x star, is equal to the same slope as the chord. Now, we can rearrange this particular expression so that we solve for f of b, and f of b is simply f evaluated at a plus b minus a times f prime x star. In other words, the slope of that line of the curve f of x. So this we refer to as the mean value theorem. And I didn't mean to erase that. The mean value theorem is a special case of Taylor's theorem. And we can approximate any function f of x by a general polynomial function as follows. So we have f of x is approximately equal to the function of x, where we choose a polynomial of degree n. So we get a0 plus a1x plus a2x squared plus an times x of n. We denote that by f of subscript n of x. So we can approximate f of x at point x0, where we have that x of 0 is equal to 0. Then we find that a0 is f of n0, which is equal to f of 0. So the derivatives of the function f of x, where it's an n degree polynomial, we set those equal to those of f of x at x naught equals 0. So then we get the first derivative is given by a1. All right, the first derivative of that term is a1. First derivative of this term is 2a2x, and the derivatives are given by a1 plus 2a2x plus 3a3x squared plus ... 2 plus the nth derivative, n times a of n times x raised to the power n minus 1. Then we take the second derivative, which is simply the derivative of this function, and that gives us this one. All right, so 2a2 plus 6a3x, and so on till we get n times n minus 1 times an x to the n minus 2. And we keep creating these derivatives because, remember, this function is continuously differentiable. So we take the nth derivative of this function, and we get that it's n factorial times a to the subscript n. Clearly, when x is 0, we get a1 is f prime 0, a2 is the second derivative evaluated at 0 divided by 2 factorial, and we keep going, an then is the nth derivative evaluated at 0 divided by n factorial. And if you'll recall, any factorial is simply n times n minus 1 times n minus 2, and so on till we get 1. We get then that this function f of n of x is f evaluated at 0, the function evaluated at 0, the first derivative evaluated at 0 times x, the second derivative evaluated at 0 divided by 2 factorial and times x squared, and so on to the nth derivative evaluated at 0 divided by n factorial times x to the power n. And we take the limit as n approaches infinity, which is then f of x, where f of x is simply this expression here, but then taken to infinity. So f of 0, f prime evaluated at 0 multiplied by x, second derivative evaluated at 0 divided by 2 factorial times x squared, and continued infinitely. And we call that a Maclaurin series because the expansion is about x0 equals 0. Now, a Taylor series is just a more general version of that, where we evaluate f of x at a point x naught. So we choose now to expand our function around the point x naught. Now, this is a way that people do all of this, and what you're expecting is that somewhere along the line x of naught might be your solution to a numerical problem, for example, given by the function evaluated at x of naught, the first derivative evaluated at x of naught, times x minus x naught, plus the second derivative evaluated at x naught, divided by 2 factorial, times x minus x naught squared. Remember, if x naught was 0, then we just have the x squared like we did up here, for example. And then we add to that the third derivative evaluated at x naught divided by 3 factorial times x minus x naught to the power 3. And we continue that kind of forever and determine some kind of a truncation along the way. So a useful form of the Taylor series includes Lagrange's form of a remainder. So that's an important thing to keep in mind, that once we truncate it, we have a remainder. So let's say we were to truncate this one at the second polynomial, then all of this, including this infinite stuff, has to be put into this remainder. So a finite power series can be exact under suitable continuity assumptions where the last term is evaluated at x star, which is between x and x naught, rather than evaluated at x naught. So we get f of x is equal to f, the function evaluated at x naught, first derivative of the function evaluated at x naught, x minus x naught, plus the second derivative evaluated at x naught divided by 2 factorial times x minus x naught squared, and so on until we choose some n to truncate it at. Now that n could be 2, let's say, in which case that would be the term we're looking at. So this last term is then the nth derivative evaluated at x star rather than x naught, and then divided by n factorial times x minus x naught to the power n, where x star here we define as a point between x and x naught, so x naught plus theta x minus x naught, and theta is between 0 and 1, although it can take on the values 0 or 1. And we know that this exists. The nth plus 1th derivative is continuous, so it's all these derivatives are available. So the mean value theorem then is a specific form of the general Taylor series where the expansion is terminated at the first derivative of x star. So it looks like this. F of x is f x evaluated at x naught plus the first derivative of the function evaluated at this x star, where x star is determined as, you can see that you evaluate the f of x naught plus the first derivative evaluated at x naught plus theta x minus x naught, all multiplied by x minus x naught. And if you compare that to the mean value theorem which we had, which was f of b, which is here our f of b, evaluated at f of a, which would be that term, plus b minus a times f of x star.